Dear student, welcome to class. In last lecture, we had discussion about flooding of data in mobile network. And today we will have discussion about flooding of control packet. As you know that flooding of data and control packet together increase overall communication overhead inside a network. There are many protocols which perform flooding of a control packet instead of data packet. Let me explain it here on the whiteboard that inside a packet we have two types of data. One is related to control information, and this control information include the sequence number of packet, that include the sender ID, it include the receiver ID, and that include also the checksum, or you can say the CRC, or some other important parameter as well. So this is the control portion of this packet. Another portion of this packet is called the payload. So payload is the actual data which we want to transfer, which we want to send. While payload is the actual data that we want to transfer. So therefore, if you can see in simple flooding, we were going to broadcast both control as well as the payload, the actual data. But now in control flooding, we will only transfer the control information inside this packet. And for example, if we can take the size of this frame, or this packet is 50 KB, out of which 5 KB is control data and 45 KB is the payload. So you can see by transferring or broadcasting only control information, which is 5 KB, we are reducing the network traffic. We are reducing the network traffic only in this one frame by 45 KB. So therefore, this mechanism will reduce the network overhead. This is the first point. Similarly, it will also provide security to information that we want to share, as the data will not be exposed to all nodes inside the nodes. And another thing is that it will also increase the nodes, or you can say the network life. because they will do less processing. So it will also reduce the computational cost. So look at this. This is the main mechanism that uh, we are going to follow to only share the control information and the control packets. So here you can see that the control packets will be used to discover the route, and these discovered routes are subsequently used to send the data packet. Once the route is discovered with the help of control packet, then we would be able to transfer the actual payload or data to the destination node. Overhead of control packet flooding is amortized over data packet transmitted between consecutive control packet flood. And as I told you earlier, that this control packet sharing by these protocol definitely provide some security as well as reduce the network overhead and the computational cost. Now moving next to the DSR protocol, you can see here that the next protocol we have is the dynamic source routing. DSR is another protocol that totally depend on the source to provide the route information. Now we will follow the same example that we discussed earlier in the flooding protocol. When a node S wants to send data to its desired destination, but it don't know about the route toward that destination, then it will initiate the route discovery process. And in this route discovery process, the node source will send uh, route request, which is a specific packet that is used for route discovery and will be shared with other nodes. Similarly, every node will which receive this routing request will append its identifier and will forward it to the neighborhood nodes. And then onward, the same process will be followed by the next node inside the network, and then will be forwarded to the next neighborhood node. You will also see this in this example here, where we have a route discovery for the DSR protocol, in which we have node S, and here is the destination node D, and route to destination node D is not known to node S. So therefore, the sender node S will prepare a route request and will flood inside the network to its neighborhood node. So the neighborhood node will append their ID inside that packet and will forward it to the next node. So let's start this process that the sender as well broadcast the transmission of route request to its neighborhood node. And in this case, you can see that the neighborhood nodes are B, C, and E. So all the three nodes will receive these packets. Similarly, the list, look at this, this is the list which is started from S and then onward will be maintained by all other nodes. So as the packet is received by E as well, then it append its own ID, which is E here in this list. And similarly on this side is C node, it also append its ID here, and then a list is prepared. You will only focus on this side of a network as the destination node lies here. In this direction, we will a bit ignore these A, B, and H protocol and not prepare the list for this, though they will also follow the same rule. So here the list is prepared to S, C, and SE. And now the packet or the route request is forwarded to F and G. And here you can see that F also append its ID here in the list, and same is the case with the G. Now the data is forwarded to J and K to the next neighborhood nodes. So node C actually when received the route request from G and H, but doesn't forward it again. Here in this situation, you can see that the C also received the route request from G and H. And the main reason behind that is that C already forwarded the route request to its neighbors. And C know about this packet from the sequence number that is used here inside the packet. Now, J and K also append their ID and forward their data to the destination node D. And here you can see that SCGK is received from CG and K from the lower route, and the upper route is SEFJ to the D. Similarly, SEFJ route request is also forwarded to M because M also comes in the neighborhood of this node. So node J and K both broadcast the route request to node D, and sometimes there is possibility that the packets transmitted by J and K may collide over here because of the hidden terminal problem. There is possibility that the transmission may collide and node D don't receive any packet from node S. But there is also a possibility that there is some time difference between the transmission of node J and K, and D received both packets or both frames. So once the D received both frames, then he will decide based on the parameters or based on the time slot that to which node he should respond earlier. On the other side, the packet was received by M, and similarly, M followed the same algorithm and append its ID inside the list. And the complete list now contains S, E, F, J, and M. It is received by L, and L actually send it back to the M. And as M know that he already forwarded this route request, so therefore he stopped this process. Now, you can see that node D doesn't forward the route request. And the reason behind that is that node D is the intended destination for this route discovery. So therefore, node D have now the information about both routes here from S, E, F, J, and then onward to D. And from the other route, he has information about S, C, G, and K to D. So now the node D will decide that either he should reply to J or K about its destination node. So about its route that he has selected. So now the route discovery almost reaches to the destination node. Destination node receives the packet from node J and K. Now the destination on receiving the route request will send the route reply. Now this route reply by itself is a specialized or a specific packet that also contain the control information about these nodes that which routes or which nodes will be a part of this communication. So route reply is sent on a route obtained by reversing the route appended to the received route request, and therefore the same path will be used, and but it will be reversed in other direction. Now route reply include the route from S to D on which the route request was actually forwarded and received by the destination node. So here in this example, you can see that D has selected. We can also imagine that D replied to J based on the timestamp. As request from J was received earlier instead of K, therefore D replied to J about its finalization of this route for communication with S. So now the D use the same list which was received from S and use it in the reverse direction. So D now send first its route reply to J, then onward to F, and then onward to E, and then onward to S. So now S actually received the route reply, and this route is recommended by D to use for communication. So here you can see now on the next slide that after receiving the route reply that was sent by node D is finalized. So route reply is sent by reversing the list that is obtained by the route request. And it is only possible if we imagine that there are bidirectional link inside the network. For example, if it's a unidirectional link, then the node D will also perform the same route discovery process from D to S. And it will not follow the same route because it's a unidirectional route. Therefore, the next route will be used. And in case of IEEE 802.11, we actually know that the links are bidirectional. So therefore, the same link is used for data delivery as well as for acknowledgement. Now here you can see that node S on receiving the route reply caches the route included in the route reply. And therefore, uh, the same route will be used for future communication. When node S send a data packet to D, the entire route is included in the packet header. Therefore, it is also called source routing. Now, this is very important to know that why it is called sorry, why it is called source routing. So it is called source routing because the source is responsible to define the complete route and provide all the necessary information to the available nodes inside a route. So therefore intermediate nodes use the source route, including node will use the source route included in a packet to determine to whom a packet should be forwarded. So all this information is provided by a source node, and there is no authority with the intermediate node in a route, in a link, that it should decide by its own to change the route. So therefore, the nodes, all the nodes are responsible that they should provide our transfer, our forwarded information to that node which is specified by the source node. So here in this list, you can see that S, E, F, J only follow the list to deliver data to the destination node. They don't have any authority to bring any change to the packet size. But there is one drawback of this technique is we have a large network, then the packet size will grow for a long route. Therefore, DSR is not recommended for long network because then the control packets will grow automatically much more. So let me explain this on the whiteboard as well. So DSR is a source routing protocol. And the main reason is the source provide all information, all info about the routes. So for example, if we have a big network with, for example, with 2000 nodes, so in that case, we will have long routes. For example, there may be 500 nodes, and the source is responsible to provide all those information about these 500 nodes to the next node inside the network. So therefore, DSR is not recommended. DSR can perform well in small networks, but not recommended for large networks. And the main reason behind that is that the control packet or the control information will drastically grow, and might be there is possibility that control info have more size than payload or actual data. So this is very important thing to know, that DSR is good protocol considered in small networks. So here in this slide, you can see that now the same route which was decided by node D. So look at this, it is the prerogative of node D to decide that which node should be used for data delivery. So here node D selected J, F, and E that should be the part of this communication process, and they can play the role of forwarding node. Now, when the route discovery is performed, this is also a very important question, that when node S want to send data, then the route discovery will be performed. So, but it doesn't know a valid route, and therefore it will start the route discovery process. So based on this mechanism, DSR, we have like a reactive protocol that it start the discovery process whenever there is data with source node. Now here is another important thing, that is the DSR route of optimization and route caching. So DSR actually saves some data in its cache. All the nodes are responsible to save information about their neighborhood node. So therefore, each node will cache a new route. It learns by any means from the neighborhood or from any other node. So therefore, when there is a route discovery process from source to destination node, all other nodes that comes in between node S, which is the source, and node D, which is the destination node, they also know about other node. So therefore, you can see when node S finds route S, E, F, J, D to node D, node S also learn that there is a route from S, E, and F to node F. So if he send a data to node E, it will be delivered to node F. So there is possibilities that in future, node S might want to transfer some data to node F, so he can send it to node D. Similarly, when node K receive route request SCG destined to node, then node K also learn that there are some other nodes which are G, C, and S, which means that now if K want to communicate with these nodes, they can easily transfer data to them via node G and C. When node F similarly forwarded the route reply, then it followed the path of SEFJD. Therefore, node F also learned about the route to node D from F, J, and D. And these are some additional information. Similarly, node E also learn about its neighborhood nodes that are F, J, and D. And in future, if it it needs to deliver or to transfer some information to node D, to node J, to node F, then it's already know about these nodes, that where they are actually placed in this network. Therefore, the node also learn the route when it overhear about the data packets from the surrounding node. So this is not always the process that you will do the route discovery for every node. Sometimes because of this route caching, while performing a route discovery for some other nodes, you may find that who are actually in your neighborhood, and in future you don't go for route discovery unless and until there is no major change, there is no movement and mobility inside that network. You can use those routes to deliver your data to the desired destination. So when node S learn that a route to node T is broken, it uses another route from its local cache. If such a route to node D is exists, then it will also be available over there. So when such a route exists in the cache, then it can also use this data. Otherwise, for example, if there is no route available, then node D or node S will perform the route discovery process. And as we discussed earlier, that normally we consider while using 802.11 protocol that these routes or these links are bidirectional. For example, if these links are unidirectional, then node D will also perform the same route discovery process is followed by the node S. So node X on receiving a route request for some node like D, it can send a route reply if node X known a route to node D. So this is actually the responsibility of an intermediate node. If it knows about the destination node, so it should reply from that position. So here you can see, for example, here in this example, you can see that we have node S, then E, and then node F, and then J, and then D. For example, this is the route. And now another node come here, which is node P. And node P also want to send data to the destination node, and it send a packet to node E that I want to communicate, I want to transfer data to node D. So as in this situation, node E already know about node D. So therefore, node E will reply about node D that yes, I know about node D, and I can provide access to node D with 3-hop or 2-hop, or you can follow this path Fj, and then node D will be available over there. So this is actually the response of intermediate node, uh, which know, or you can say that node in the middle, which know information about the desired node. So as the information are known to node E, therefore node E provide information to node P instead of doing the same broadcast mechanism again. So now moving toward next slide. Look at this. Now you can use the route cache and it can speed up the route discovery process. And similarly, it can reduce the propagation of route requests. And as we discussed in the last example, that node P is looking for node D, and he sent his route request to node E, and node E already know about node D. So therefore, node E forwarded the available route information to node P, or you can say it shared the available information about node D with node P. So this actually reduce the network overhead as node E intelligently play its role and didn't broadcast the route request of P to other nodes. Now here you can see the use of route caching, that node S knows about E, F, J, D. Similarly, E know about F, J, D. Similarly, F know about F, J, D. And similarly, F, E, S. It also know about F, E, S. And J also know about F, E, S. And same is the case with G, C, and K. So therefore, these labeling or these lists actually represent the routing table of these nodes, that which nodes are known, are accessible from here. So these label actually represent the cached route inside every node, and it is maintained with the help of DSR protocol. Now here you can see, as we had example earlier about node P, the same example is given here, that when node Z, which is here, it sent a route request for node C, node K send back a route reply with Z, K, G, and C. So here is the node Z, which want to communicate with node C. So it prepare a route request and broadcast it, which is received by its surrounding or neighborhood nodes K and D. Ace can know about the destination node C, therefore it reply back and send the complete information about this route, that you can access a node D with following K, G, and C, and therefore node Z, after receiving this information from the locally cached route at K, get this information very easily, and he didn't perform the complete route discovery process in the whole network. So this, therefore, this storage of cache or caching of this route information on intermediate nodes or in the middle nodes are very helpful to the new nodes that join the network later. Or sometimes there may be a possibility of different modes of these nodes, as the node may go to the sleep mode and he don't know about that which is the new node available in the surrounding now. So by sending a route discovery or a route request, the neighborhood node are responsible to provide information. Now you can assume that there is no link between D and Z over here. Therefore, route reply from node K limit flooding actually here as well. If, for example, if node K went for flooding, then therefore all these nodes and surrounding will receive this route request, and then onward they will forward it or send it to their own neighbors, and then onward to the other neighbor as well. And then the destination node is like the previous example, while receiving the route request from node G, they will prepare the route reply and will send it back. So this is a very lengthy process. Therefore, the intermediate node, which is K in this situation, play a very intelligent role and provide information from its own cache. Now here is another problem of a router. Sometimes the link may be broken because of some collision. There may be some situation in which the node moves from one location to another location. Here you can see in this example that J to D link is broken. Therefore, the responsibility of G is that it should send a route error to node S, to source node, along the route that is J, F, E, S. And when it attempt to forward data packet, then it should know that node J to S D is down. So this node J play a very vital role in this process, because node J is informing all the other nodes in this route that node J to D link is down, so it can stop the traffic from the backside from node S. And another process is that it also start working to repair this error as well. Therefore, all nodes J, F, E, and H which hear about this route error will update their cache as well. And therefore, they will remove node J to D as it is down from their cache. Otherwise, if they still keep this information, then that will be outdated information and it can misguide all the other nodes inside the network. So look at this, the stale cache can adversely affect the network performance as well. Stale cache means that you are saving outdated information as the link from J to D is now down, it is not available, and you still store those information inside your cache. Similarly, with the passage of time and host mobility, the cache route may become invalid. Therefore, it is responsibility of the nodes that they should update their cache information and keep the recent location or the recent neighborhood nodes ID with themselves, or the list of nodes that actually comes inside a route or a link from source to destination. When a sender host may try several stale routes obtained from stale cache or replied from stale by other nodes before finding a good route. So, for example, if there are some outdated information that are stored, then it will be disseminated to all other nodes inside the network, and it may pollute all the caches of other nodes inside that network. So, all those nodes will have the wrong information, and therefore no packet will find its destination. Here are some advantages of this DSR protocol. The first one is that it maintains routes only between nodes who need to communicate. So therefore, routes are established and routes are maintained only in that particular area on those specific nodes which are involved in that communication process. And all the other nodes which are not in the communication are not part of that communication process, they will not store the list of nodes or the route information. So it reduce the overall overhead inside the network, as well as reduce the route maintenance. Similarly, the route caching can further reduce the route discovery overhead as well. The route discovery overhead is reduced as the intermediate node can provide information about any node they know. A single route discovery may yield many routes to the destination due to intermediate nodes replying from the local cache. So the local cache is maintained by the intermediate node may provide some good information about the desired destination, as we discussed in the last example. When node P want to discover a route to the destination node D, then node E actually helps to provide the routing information. And here are some disadvantages about these uh, protocol, about the DSR protocol. And as we discussed earlier, that it is considered as a good protocol for small network. But for large network, the packet header will automatically grow, and therefore, as the route length will increase, so the control information inside a packet will also grow. So sometimes there may be an imbalance situation that the actual data that you want to transfer to destination node is less than the header size. So therefore, we avoid to use DSR protocol in large network. Similarly, the flood of route requests may potentially reach all nodes in the network as you are going for flooding. So therefore, there is possibility that it may potentially reach all nodes inside the network. Similarly, care must be taken to avoid collision between route requests propagated by neighboring nodes. So as they are involved in flooding, therefore, we should try the procedure by uh, by intentionally adding some delay to the neighboring nodes that they should not send or broadcast the route request at the same time, so they should avoid the collision. Insertion of a random delay before forwarding a route request between the neighborhood node is very important. Similarly, you should increase contention if too many route replies come. For example, if there are too many route reply, that is some sort of bombardment on the desired node, then there is also possibility of collision. So instead of this broadcasting, you will also receive too many replies from the intermediate node and some other nodes, which may yield to the broadcast storm problem. And here you can see that route reply will sometime create the storm problem, that everyone or every node in the route reply and come back due to this local cache information that are stored on these nodes, and it may cause some collision, and the node may miss some important information because of this contention. An intermediate node may send route reply using a stale cached route, thus polluting other cache as well. So, for example, if a node has some outdated information and is shared with a new node that is looking for its desired destination, so it may pollute information, because that new node will also share those outdated information with other nodes, and automatically it will spread across the network. Therefore, this problem can be eased if we have some mechanism to purge potentially invalid cache route is incorporated. So, for example, if we use some mechanism to check the validity and invalidity of these caches, that either all the entries available in these cache are updated or not. And some of the proposal for this specific task and cache validation is the static timeout, which is, for example, after every 5 minutes, you have to upgrade your cache, you have to get fresh information. But this is not also considered a very good technique, as it will also increase the network traffic when specifically in such scenario where the nodes are not very dynamic, they are static, they stay longer at certain position. So after every 5 minutes, you are initiating this process to update your cache or to provide fresh information. Another one is adaptive timeout based on the link stability. Unless and until the link is stable, you should not ask for update. Once there is some movement, there is some change in mode, for example, someone is going in sleep mode, then you should initiate this process as per requirement. So therefore, as we can see, that flooding of these control packet actually reduce the network traffic and increase the network life. And now we will be moving in other domain, that instead of sending control packet to all nodes inside the network, we will first discover the position of our desired destination node, and then we'll do a targeted operation by specializing or specifying an area in which our desired destination node exists. So then it is the next step that we will check the location, and then onward flood or broadcast the control packet in that particular region. So therefore, how to reduce the scope of the route request flood? We have the location aided routing, that is LAR, and then the query localization as well. And another one important thing is that how to reduce redundant broadcast. The broadcast storm problem will also be addressed. So this is the end of this lecture. And if you have any question, you can ask. So thank you so much.